In this presentation, we're going to continue our recap of the fundamentals of programming, and this presentation is dedicated to control structures. And of course, we're going to be reviewing the selection and iterative control structures, things like the if statement, the switch statement for selection, and also the for loop, while loop, and do while loop for iteration. And then we're also going to have a look at logical operators, and, not, or, etc., as well as arrays. And then we're going to review some additional information regarding how to generate random numbers, as well as enumerate types, static casting, and also explore preprocessor directives in more detail, as we hinted at in the previous presentation. Okay, so let's start with reminding ourselves about blocks. Hopefully this should be familiar to you, that statements contained within a pair of braces are known as a block of code, and this may contain one or more statements which are executed in order. Remember that the compiler starts at the top of that block and then works its way through each statement consecutively. So, of course, the order that we write our statements will dictate the order in which the statements are executed and how the program runs. And if we were to change the order of those statements, we might well get a very different program based upon that new order of statements. Okay, so the order does matter and does directly affect how the program runs. It's possible that you might have the correct statements, but they might just be in the wrong order. Okay, so make sure you double check and think through how the compiler executes each statement step by step. And in this presentation, we're going to go on to use blocks to do with if statements and switch statements and other iterative statements as well, such as the for loop, do while loop, and while loop. But these braces, you will also find them in functions. As you know, we saw that in the main function in the previous presentation. And of course, we use a pair of braces for a class as well when we define one of those. And we're going to see how those braces apply to the if statement in just a moment. But just before we look at that, let's remind ourselves about the basics of using an if statement and selection statements in general. Hopefully you know and you remember that using a selection statement allows different paths through a program. It allows you to section off a block of code, or sometimes even a single statement, which is only executed providing that a condition is met. And of course, the reason for this is that it allows us to respond to particular events as and when they happen. So we can specify that we only want code to run on a particular event, essentially. If the user types in this keyword, or if the result is greater than 50, or if a negative value has been entered, or if they haven't entered the right information, or if they have entered the right information, we can respond to all of these different cases with code accordingly. Okay, and this condition is evaluated on a true or false basis. And this is often worked out by a comparison. We usually compare two values to see if they're equal, if they're not equal, if they're greater than or less than, based on the particular scenario, because of course the results of that comparison, the condition, will either be true or false. So therefore the logic has to make sense in terms of the scenario. For example, if we're trying to evaluate if a number is less than 0, if we've entered a negative number, we would have to say, is the number we're looking at less than 0? If it is, if it's a negative value, then that's true, and therefore we would run the code inside the if statement. And of course, this also reminds us that code that we section off to be in an if statement will only run providing that the condition is true. If the condition isn't true, if it's false, then we don't run the code inside the if statement. Okay, there's actually another case for that, which we're going to look at in the next slide. But before we do, let's just remind ourselves of the syntax towards constructing an if statement. And if you cast your eye to the bottom of this slide, you'll actually see there's 3 different examples. There's 3 different ways of formatting an if statement. And all of them do share the initial part of the statement, where you'll notice it obviously starts with the keyword if, and then the condition will sit between a pair of brackets. So this is typically where you have a left-hand side and then a comparison operator, and then a right-hand side. So if the number variable is less than, that's the operator, 0, in the example we shared earlier, and then that comparison would sit within the brackets, okay? And that's the same across the other two formatting examples here. But then it's after the end of the condition that we see changes, because you'll notice in the first example, we can actually have the code to be run, providing that the condition is true. We can have it next to, adjacent to the condition, if it's a single statement, that is. And then also in the second box, we can have it underneath the condition. But then in the third box, you'll notice if we have more than one statement, you'll notice here we have two statements. If that's the case, they have to be specified within a pair of braces, a block, okay, like we mentioned earlier. All right, so it's worth highlighting again that for a single statement, a single line of code that is to be run, providing the condition is true, that could be either adjacent to the condition in the first example, or it can sit underneath the condition without braces in both those cases. But in the case that you have two or more statements, those would have to sit underneath in a pair of braces. Okay, so I hope that clears up the formatting and gives us a brief reminder about if statements. Let's go on and talk about the counterpart to the if statement, which I alluded to just a minute ago. It's the else statement. And this is a part of the if statement that you can specify code to be run if the initial condition was false. So say if we go back to our negative number check, if the number is not less than 0, if that condition is false, then we can specify an else condition. Perhaps it just will say an output to the screen that this is a positive number. But what that models is that we can write additional code for the false case. Okay, we can write code in the event that the condition is true. That's going to sit within the if statement. But we can write code in the event that the condition is false, and that's going to sit within the else statement, as we can see here. Okay, and again, the same rules regarding braces also apply. For single body statements, we don't need a pair of braces for the else part, and for more than one statement, for two or more statements within an else body, we would need a pair of braces. And here are just some further examples of how you could employ an if statement. So not negative numbers this time, but instead just testing ages in these cases. Testing to see whether age is greater than or equal to 18 in the first box. And if so, if that's true, then we output a message to say that this user can vote. Okay, and then in the second box here, we extend that to have an else statement where if the initial condition that's being tested, age, if that is not greater than or equal to 18, if that condition is false, then we specify a message to be output to say that this user is too young to vote. Okay, and then finally in the third box, we're just adding additional statements to both of those cases. To the if statement where the condition is true, we specify additional information to where they can vote and where they can register, and then in the else part there's again additional information. It actually works out how many years they need to acquire before they can vote. But the point here is that as there are two or more statements in both the if body and in the else body, these need to be within braces, as you can see here. Okay, so hopefully that serves as a recap of how to use an if statement. Hopefully you've used this before and you're comfortable with it. Let's move on now And here we're actually going to have a look at a variation of the if statement, and this is less common than the standard if statement or indeed the switch statement, but if you have got experience with it, you'll know it's very efficient at what it does, and it actually goes by several different names. It can be referred to as the arithmetic if operator, otherwise the conditional operator, or is even referred to as the ternary operator because it takes 3 arguments. If you have a look at the green box here, you'll see that it takes the condition, which evaluates to true or false, like a standard if statement would test, as one of its arguments, and then after the question mark it takes another argument, which is the result to be returned if the condition evaluates to true, and then there's a colon, and then after the colon there is the third argument, which is the result to be returned if the condition is false. Okay, so it's actually a very compact way of doing if and else within one line, effectively, where you have the condition and then the true result and then the false result, okay, or the code to be executed if it's true or if the condition is false. All right, so let's have a look at the blue box here, and you'll see an example of that. So in the blue box, we have 2 integers, x is 1 and y is 2. And then the line below implements the ternary operator, where you see the condition, the evaluation of if x is less than or equal to y, question mark, and then x colon y. So x has the value of 1, and y has the value of 2, so x is less than 2, therefore we'd return the true part, the result which is after the question mark rather than after the colon, because that's the result to be returned if the condition's true, so we return x. Therefore, lower will have the value of x, which is 1, and that's output to the screen in the third statement. Okay, so this is just a more compact way of performing an if and else operation. All right, so if you get used to the syntax, this can be a very efficient way of performing an if and else statement alternative. However, of course, you can write these out as a standard if and else statement, as you saw previously. And the final selection statement we're going to have a look at in this presentation is the switch statement. And this is another common alternative to the if statement. But unlike the if statement, which compares 2 values to work out whether that condition is true or false, the switch statement operates slightly differently in that it tests the variable, tests a given storage location and the values that are stored within it, i.e. a variable, against particular cases within the switch block itself. So you'll notice here in the green box that instead of having a comparison taking place, there is just a statement of an expression. That might be just a variable name, for example. And then the values for that variable are then compared against particular cases, particular values, which might be the right-hand side of the comparison in an if statement. And each of those cases are evaluated separately. So the value for the variable is compared against the first case, and if that's true, then we run the code which is specified after the colon for that case, but if it's false, we then evaluate the next case, and so on and so on. Okay, and here the default case is the equivalent of the else part of the if statement. It means if all the above are false, then do this as a last result, and it specifies some code to run in the event that all the above are false. Okay, and so these cases are contained within the braces for the switch statement, and you'll also notice that the cases also are accompanied with a break statement. And this is to avoid the fall-through mechanism of the switch statement, which is a rather strange feature of the switch statement, in that if one of the cases evaluates to true, then that actually executes the code from the other cases below it. So it's a rather strange feature as to why that was included, because surely the idea is to actually evaluate each case on its own and only run the code that corresponds with that particular particular case. You don't want to be running other code that corresponds to other cases. But the way around this, and what has been commonly modeled over the years, is to include the break statement after the particular case that is true in order to escape the switch block and then run the code underneath that switch block. But despite this peculiarity, the switch statement is actually very effective for when you're trying to provide code to respond to a set number of defined cases. As we see in this example here, where the values will only ever be 1, 2, and 3, we can actually set up specific cases to respond to case 1, case 2, and case 3. And then the default case would be basically anything other than 1, 2, and 3. And then this technique will actually scale well for a large number of cases as well, because it's very compact here. Whereas if you're having to write a lot of if statements, whilst you can do that, there's going to be a lot of repetition there, because you're going to have to include the variable every time you do the comparison for else if statements. And here it's quite a compact way. If it's only a single body statement, that can be put on one line. And I think technically the switch statement is slightly more efficient in memory than an if statement. Okay, for a large number of cases, we're talking, I think, 20 or above, the switch will actually outperform the if-else block, I think. So switch is definitely advisable in those cases. However, it does have drawbacks in other areas, because it's only useful for defined number of cases. It doesn't handle ranges that well. You can actually use the colon in successive cases on one line. So you could say case 1, colon, case 2, colon, case 3, colon, basically saying if it's either 1, 2, or 3, but it doesn't do and very well, because it's set up to evaluate particular categories. So in this case, obviously the value entered can't be 1 and 2. It can only ever be 1 or 2. Okay, but hopefully this just gives you a recap of the switch statement. As I say, it can be very effective in certain situations, mainly when you have a defined number of cases and lots of them. So that concludes our recap of selection control statements. Let's go on now and have a look at iterative structures. And so let's talk about the while loop first of all. And the while loop, like all other iterative statements, will repeat the code within the braces, the actual body of the loop, whilst the comparison that's being checked evaluates to true. And of course, this differs to selection statements that run the code inside the braces only once if the condition is true. Okay, so remember that difference. Selection will run once if the comparison is true, but while loops and for loops and iterative statements will repeat the code whilst the comparison is true. Okay, so there's a key difference there between iteration and selection. And the while loop, as we see here, the pseudocode in the green box, starts with the keyword while and then has the brackets followed by an expression, where this could be an evaluation of two values. It might compare if they're greater than or less than or the same or not the same, or it may simply just be the keyword true, the Boolean value true, meaning that this would be an infinite while loop. If that true never changes, or we never break out of the loop in a separate case within the body of the loop, this would run forever. And of course, we have a pair of braces following that expression where we place the code that we want to repeat inside the body of the while loop. And the same rules apply. If we've only got one statement, a single line body, then we don't need a pair of braces. But if we have more than one statement in the body, then we do need a pair of braces. And so you'll notice that in the first green box, the while loop evaluates the condition before we run the code inside the body of the while loop. But a do while loop, as you probably remember, has that comparison, the evaluation, take place after the body of the loop. If you cast your eye to the second green box, you'll notice that the do while loop starts with the keyword do and then opens the braces without checking the comparison, without evaluating an expression. And this means that there's no check on whether we would actually perform the statements inside the body of the loop first of all. So that means that we're always going to run this do while loop at least once because of the order of the statements. Remember, the first while loop, the standard while loop, will only run the code if that condition evaluates to true, and that's checked first of all. But in the do while loop, that condition is actually checked after the body of the loop. Okay, so we actually run that code in the do while loop at least once before checking. Even if that comparison evaluates to false, we're always going to run the body of the loop at least once. And you might wonder, well, why might we use this do while loop? Well, it's actually useful for validation, where you might want to perform the particular task, whether it's asking the user to input some data, first of all, before you check it, because obviously you don't have access to that data if you're asking the user to input it. So you need to get it first and then check it. So that's a good use for having the condition take place after the loop body rather than before the loop body. Okay, so this is a really useful structure for checking and performing validation, the do while loop. You might well have used it before, perhaps in previous programs, but if you haven't, have a chance to have a go at it in some of the exercises for this week. So that's the difference between the while loop and the do while loop. It's the order, of course, will actually affect the logic of the program. So just worth bearing that in mind. Let's go on and have a look at the for loop now. And like the while loop and do while loop, there is actually another variation of the for loop. There's something called the for each loop, which you may be familiar with. That's actually a particular type of for loop, which will loop through every element in a data structure. That might be an array or a vector, and you can declare an element within the for each loop, and then for every element in the data structure, you can then perform a task. And that's quite convenient because you don't actually have to know the size of the data structure. It'll automatically just keep going until it's checked every element within the structure that you've specified to look through. So that's very useful when trying to perform on data structures. But here we actually see a standard for loop where you actually set it up to repeat a defined number of times that you specify. Okay, so it's not dynamic like the for each loop. Instead here you specify a certain number of times that you want this loop to repeat, and the for loop will repeat that for you. Okay, so here in the green box here, we see the pseudocode, which typically has 3 parts within the for loop. We have to initialize a counter variable. We typically see the letter I being used. It's an integer variable, so you'll typically see int I. We usually start it at 0, unless there's some specific case where it needs to be something other than 0, and then semicolon, so that's an actual statement, so we have to declare a variable int I equals 0 semicolon, and then we would set up the condition where we specify how many times we want to repeat. So if we started I at 0 and we wanted to repeat this loop 5 times, then we'd have to say whilst I is less than 5, and then semicolon again, because then what we're going to do is we're going to increase the value of I upon finishing every iteration of the loop. So this increment part, the last part, which note doesn't have a semicolon, that is how we're going to change the loop counter so that we know how many iterations have been completed so far, the value of I, the current count, and we also then use that to compare against the limit, whether that's 5 or 10 times, 20 times, 25 times, whatever that might be. Okay, so if you step it through, I starts at 0, I is less than 5, so that's true. Therefore, we run the code inside the for loop. Once that's finished, we then increase I to 1, because it's I++. Then compare against the condition again. 1 is less than 5, so that's true. Do the code again, and then increase it to 2. 2 is less than 5, therefore do the code, so on and so on, until we get to 5. And then 5 is no longer less than 5, so that's false. Therefore, we don't run the code inside the braces, and we exit the for loop. Okay, and you'll see that in the blue box below. Okay, so hopefully that's been useful revision there on the iterative control structures, such as the while loop, the do while loop, the for loop, and the for each loop as well. Let's move on now and have a look at another subject. Let's talk about logical operators. And again, hopefully this is familiar to you if you've used them in if statements before. But just to remind you that we have a few different logical operators here. We've got the logical not operator, which is the exclamation mark, and you might be familiar with the not equals to operator when you're checking to see whether something might be not equal to null, for example, checking to see if something does exist in an object or in a particular structure. So you might be familiar with it in that circumstance, but the not operator can exist outside of a comparison. Here, if you notice the first blue box, we're outputting a comparison of if 3 is greater than 1. And in the first line, that displays true. But then in the second line, we've actually put the not operator in front of that comparison. Therefore, whilst the evaluation would be true, that's then flipped to become false, because we're actually checking the opposite of that comparison. So therefore, something that evaluates to true is then flipped to be false, and vice versa, something that evaluates to false is then reversed to become true. Okay. The next operator we see here is the logical AND operator, and you're probably familiar with this when you're comparing two or more conditions in an if statement perhaps. And again, this performs in the same way. You'll notice here in the second blue box that both comparisons are required to be true in order for the overall evaluation to be true. Okay, so in the first line of the second blue box, testing to see is 3 greater than 1, that's true, and is 3 less than 10, that's true. So therefore, overall, the evaluation is true. But in the second line, is 3 greater than 1, that's true, but then is 3 less than 1, that's false. So therefore, the AND operator, it specifies that both have to be true, or every condition has to be true. Then because one is false, then overall, the evaluation is going to be false. Okay, but then the logical OR operator, the third and final operator here specified, means that any one of the conditions can evaluate to true for the overall expression to evaluate to true. So even if we're comparing 5 different expressions, but only one of them is true, then overall the evaluation will be true. Okay, so we'll see here we've got the exact same comparisons taking place in the third box as the second box, but because we're using the OR operator on the second line, that does evaluate to true, even though the second one is false. The overall expression is true. Okay, so hopefully you're familiar with that. Let's move on and talk about the next topic, which is arrays. And we're going to start by talking about static one-dimensional arrays and then go on and explore multidimensional arrays as well. And in a later presentation, we'll also look at the difference between a static array and a dynamic array. But for now, just know that static arrays have a fixed size. That's where we declare how many elements that the array is going to contain. Whereas for dynamic arrays, we can actually assign the size of the array at runtime. So for now, let's just focus on static arrays, and we'll cover dynamic arrays in a later presentation. You'll see here that the format for declaring a static array is declaring the type, the data type that we're going to store values for. In this case, in the blue box, it's integer, so we have to declare it to be of integer type. Remember, C++ is a strongly typed language. We can't have a mixture of types. We've got to store values of the same type within a structure. Those are integer values in this case, and then we give our array a name, and then we have to specify how many elements that this array is going to have, the size of the array. Okay, in this case it's 5. So therefore the indexes, the individual elements, will be numbered from 0 to 4, because number 0 is the first one, so therefore the last element will be the size minus 1. So if that's 5 minus 1, that's 4 here. As you see in the blue box, the last element to be assigned a value is element number 4. Okay, and also in the blue box, you'll see an example where we're just assigning values for the 5 elements and then just printing them to the screen. And also, it's worth knowing that the array name itself, in this case it's marks, is actually a constant pointer to the first element in the array. So if we just briefly refer back to the previous slide, you'll notice that the 0th element, the first element, had the value of 40, and the marks array, the actual array name, holds a pointer to that element, the 0th element, the first element of the array. So if we were to dereference that by using the asterisk, remember that's the operator that's used to access the value at a memory address, we'd actually see the value for that first element printed to the screen, okay, which would be marks element 0. Which would be the value of 40. All right, but remember we said in the previous presentation that arrays are a contiguous block of memory, i.e. when the compiler allocates the memory from the stack, they're all related. So all the individual addresses are allocated as consecutive cells. And if it's a block of memory addresses that will store integers, then those will all be 2 bytes apart, because remember that's the size of an integer data type which is allocated in memory. So therefore the first memory address may, for example, end in 50, but then the next element will be end in 52, and then the following element 54, 56, 58, 60, 62, 64, etc, etc. Okay, so all the elements will be 2 bytes apart, so therefore if you know the address of the first element of the array, then it's easy to then access the following elements simply by just pointing to the next memory address in that block of memory. So this is actually known as pointer arithmetic. And this doesn't technically add the integer value of 1 to the memory address, because that memory address isn't actually an integer, it's a hexadecimal value. Instead, it just signals that we need to go to the next memory address in that block of memory which is allocated to the array. So remember, that's what is going to be taking place here. But this does allow us to, in this loop in the blue box, allows us to access all the consecutive addresses for those elements, and then we dereference them to get the value stored at those elements. Okay, so this can be a powerful technique and a very efficient technique to get direct access to array elements from the address of the first element, which is of course the array name. Now let's talk about the initialization of array elements. And you remember back to the previous presentation when we said that to initialize a variable is to assign an initial value to it when it's declared. It's the same here with arrays, but there's actually a difference between the initialization of global arrays and local arrays. If you declare an array to be global, then the elements for that array will be automatically initialized to 0, or if it's another data type, a default value for that particular data type. That might be string or Boolean or character, for example. But if you were to declare an array in a local setting, perhaps within a particular function, then this wouldn't happen automatically. But regardless of whether the array is declared to be global or local, there is actually a convenient way to initialize default values for arrays in both settings. And this is particularly useful when you know the values for the array elements, because then you can assign them far more efficiently in one pair of braces, as you can see here. You'll see in both the green box and the blue box here that you can encase the values within a pair of braces separated by commas. And of course, if you don't declare the size of the array, then the array size will be inferred from the number of values. So if you specify 10 values, then obviously the compiler will know that there's going to be 10 elements, which will be ordered from 0 to 9, which would be numbered from 0 to 9. Okay, but if you do specify the size of the array at declaration, then obviously you can't exceed that in the individual element values that you include separated by commas within the braces. Okay, so you can't have more than your size. That still applies. But still, this is going to be a far more efficient way to assign values if you know them at declaration, rather than having to have lots of consecutive statements where you refer to the individual element and then assign it a value in a separate statement. Next, let's talk about multi-dimensional arrays. You may have some familiarity with 2D arrays, 2D being short for two-dimensional. Okay, so this emulates the row and column matrix, or perhaps if you're familiar with spreadsheet software like Excel, you'll be familiar with the row and column layout of that. And effectively, that's what a 2D array is. It has one dimension allocated for rows and another dimension allocated for columns. Okay, so this is where we can create a table of either the same amount of row and columns, effectively a grid, like classic games where you have chess, that's an 8x8 grid, or tic-tac-toe, that's 3x3. Or perhaps your number of rows may not be proportional to your number of columns. You might have a smaller number of rows than you do for columns. Or you may even have what's known as a jagged array, where actually every single row has a different length and a different number of columns. Okay, so there's lots of different configurations here, but when it comes to actually declaring a 2D array in C++, we need to have two pairs of square brackets. You previously saw for the static one-dimensional array, we had just one pair of square brackets where we have one size allocated for the number of elements of that 1D array. Here, we need to have one pair of square brackets for the number of rows and another pair of square brackets for the number of columns. Okay, so you'll see that in all the examples here. And it should be said that this syntax may look different across other languages. For example, this may be just one pair of square brackets with both the row and the column inside that single pair of square brackets, but they may be separated by a comma. But in C++, it's two pairs of square brackets. And technically, there's also a difference between initializing a static 2D array to initializing a dynamic 2D array. But just sticking with the static arrays, like we looked at earlier, here you'll notice in the first blue box that we can initialize the 2D array. It's just an 8x8 grid in this case. You'll notice the two pairs of square brackets with 8 inside them. That's going to create 8 rows and 8 columns. And then we can have a nested for loop structure, a standard for loop that is, where the outer loop, the first loop, has a loop counter called R, indicating rows, and the inner loop, the nested loop, has a loop counter called C, which is short for columns. Okay, so the outer loop is the rows, which is done one row at a time, and then the inner loop is the columns. Okay, so for every row, we would instantiate each column of that row, and then move down to the next row and do all the columns. Okay, so it's going to go left to right for every row of the 2D array. Okay, and then finally within the inner loop, you'll notice the reference to the board, the 2D array with the two indices R and C inside the square brackets, and that's just initialized to the value of 0. Okay, so that's a convenient way of initializing a static 2D array, although you can also use the pair of braces like we saw in the previous slide, but you'd have to specify all the values for each row within a nested pair of braces. If you pay attention to the first blue box in the last bullet point, you'll notice that this is actually a non-proportional 2D array. You've got a larger number of rows than you have columns. So there's 4 rows, but they have 2 columns each. And for each of the rows, you have to specify the values for the columns. the values for the cells of those columns. Okay, so you notice that it's done row at a time, and the two values would be stored in those two cells. So you notice that the first row will have the values of 1 for both of the columns, and then the second row has the values of 2, third has the values of 3, and the fourth has the values of 4. And so in short, you'd have to specify all the values for each row within a nested pair of braces. Okay, you can actually omit the number of rows if you want to. That can be inferred, but you do have to specify how many columns there are in the final blue box. Okay, so there's a number of different configurations for initializing a 2D array. We'll have a look at the initialization of dynamic arrays a bit later in the module. So let's change subject now and talk about how to generate random numbers. And there's a function called rand, which exists within the standard library, which you have to include in order to access this function. But if you call this function, it returns a number between the range of 0 and this rand max constant, which is the upper limit of a signed 2-byte or 16-bit integer, which is 32,000. Okay, if it was unsigned, obviously it could be double that, but it's currently signed, so it's only going to give you the upper limit of 32,000. So you could use that to give you a random number between 0 and 32,000, or you could actually make use of a larger range of numbers to pick from using time. If you remember back to the previous presentation, we actually managed to get the number of seconds that have passed since the 1st of January 1970, which was quite a colossal number. That would give you a larger range to pick from, and of course more chance of getting a unique and a different number if you needed it every time, and also reduce the chances of getting similar numbers from a smaller range. Okay, so you could make use of that as well. And there's actually a different function which is set up to accept this number of seconds, also in the standard library, which is called srand, which actually takes a seed, if you like, a number to start with, okay, which we can pass in as the large number of seconds. And this large number of seconds can be passed to the srand function before we then perform a modulo division on that number which is returned from that function. You'll see that in the next slide. So let's have a look at this now. And you'll see here that we're actually going to be using the srand function. So that's the first line of the main function here. And you notice here that we're also including time. That's how we get access to the number of seconds. Okay, and we pass that to the srand function, which then means that we can draw from a larger number of seconds. So we have a larger range to then call the rand function. And if we hadn't have called the srand function in the first line, remember that the rand function would have had to have picked a number between 0 and 32,000. So if we call srand and pass time, as we do here, we can then draw upon a larger number of seconds. Okay, and then here's the modulus afterwards. We divide that number, which is returned, by 10. Which then means that we get a number which will be between the range of 0 and 9 if we wanted to reduce the range of numbers we want to pick from. But by having a larger range to start with, we then maximize our chances of getting a uniquely random number. We reduce the chances of getting duplicates. Okay, so I think we're going to apply this in one of the exercises later, so you'll get a chance to see how that works. Let's move on now and have a look at the next topic, which is enumerate types. Okay, you might have met these before, but if you haven't, enumerate types are a handy way to define a custom type which has a defined and limited range of named constants. Now, these go by lots of different terms. Technically, they're known as enumerators of the enumeration, but I like to refer to them as categories, just to distinguish between the enumerate type name, because the actual categories themselves can have values. They actually have an integer value in C++, then start at 0 and then increase for each category. In other languages as well, you can define other types of values, such as string values or character values, Boolean values, etc., etc. Okay, so I like to use the word categories for the individual enumerate values. And in the next slide, we're going to have a look at an example where we create an enumerate type for the days of the week. And obviously there are only 7 days in the week, so therefore there's only ever going to be a range of 7 categories, 7 values for that enumerate type. Okay, but just before we do, let's have a quick look here at the syntax, which is we have to use the word enum. That's actually a keyword, that's a reserved word in C++ when defining an enumerate type, and then we actually provide the name of it. So if we're going to use days of the week, then we could call it something like that, and then within the braces, that's where we define the individual values or categories separated by commas. Okay, and optionally, in other languages, that's also where you might assign values, the actual integer values or other types to those categories. Okay, so hopefully that will become evident. Let's go on and have a look at this example then, using the days of the week. So you see that format being applied in the first line of the blue box here, where we've got an enumerate type called days of the week, where we've defined the categories for the days, Monday to Sunday, separated by commas, and Monday will have the value of 0, and then likewise sun short for Sunday will have the value of 6. Okay, so 7 individual categories with values from 0 to 6, from 0 to 6. Okay, and then in the main function here, we've created a variable of the days of the week enumerate type called matchday. We've given it, in the next line, the value of sat, and then when we pass that to the cout stream, we don't actually see the word sat, we actually see the value, the integer value, which is assigned. And remember, these are going to be numbered from 0 to 6, as we said earlier. Even though we haven't actually assigned them, those are the default values which will be assigned by the compiler. Okay, so we don't actually see the word sat, we actually see the integer value of 5 printed to the screen. In other languages like Java, you can actually assign string values for enumerate types, but here in C++, we're actually limited to just integer values. But still, they are still a very good way of reducing the amount of validation that's required. Okay, we can still use these categories to compare against so that we don't then have to check all the other extraneous variations of the categories, such as uppercase versions of Sunday or lowercase versions of Sunday, sun, Sunday, S for short, choose, for short, all the different variations of the categories. We can actually reduce them down to just checking a smaller number of categories here. Okay, so it does still have benefits in terms of validation. As we see on this slide here, it actually improves the readability and also improves the validation. And here we see the application of the switch statement. Remember we said in the previous presentation that the switch is ideally suited towards defined and individual cases. Well, the enumerate category, of course, does have a defined number of categories which correspond to individual cases. So this is an ideal So the switch statement is an ideal way to complement the enumerate type in terms of being able to generate responses. And if you pay attention to the switch statement here, and specifically the cases, you'll notice that we're actually combining cases here. We're actually grouping them by whether they are a weekday or a weekend day. You notice here that we start with case sat and then have colon without saying anything afterwards. But then we go immediately to case sun and then have colon. And then we actually output the weekend day message. Remember, we said that cases could be combined and that the colon actually acts as an OR logic operator. So here it's saying if it's case sat or sun, then output this message. And then we do exactly the same for Monday to Friday, where we output that it's a weekday. And notice that we've only got the break statement after Sunday. And whilst the fall-through mechanism can appear confusing initially, it actually starts to make a bit more sense here, doesn't it? Because we only want to break out of the statement in the case that we actually output the message. So case sat, if it is Saturday, then we want to actually trigger Sunday, which is the message. And likewise, if Tuesday, then we want to go down to the cout statement for weekday, which is in Friday. Therefore, we don't want to break out of the statement too early. So whilst it appears confusing at first, it can actually be used to be advantageous for efficiency. We don't have to duplicate the weekday output or the weekend outputs for every one of the cases. We can actually fall through, jump down the switch ladder to the case which does actually output the message that is correct. Okay, so that's quite an efficient use of the switch statement, complementing the enumerate type, as well as the structure of the outputs there. Okay, and one final point to mention is that, of course, we can't increment the enumerate types themselves, the categories, because, of course, remember, these are constants, and even though we don't assign the values, they are assigned starting at 0, and therefore they can't be changed, so we can't increment them. Therefore, we're using an integer here to do that. Okay, that will correspond with the integer values of the enumerations, the categories themselves. And speaking of types and values, it's worth stating here again that, of course, we can override the default values that are assigned to the enumerations, the categories, as you'll see in the first blue box here, where we define those constants, the categories. We can also assign a hard-coded value at that point. As it's a constant, of course, we can't come back and change it later, but we can do it at the point of declaring the enumerate type and all of the categories for it. So here we are just assigning the values of 1 to 7 rather than 0 to 6 for the days of the week. And then you can also convert integers back to the enumerate categories, as you see in the second half of the slide. And here we're actually going to be generating a random number. So we covered this earlier, but just to remind you that in the second blue box, we are calling srand, the function, passing in the time, the number of seconds that have passed since 1970. And then using the rand function to pick from that colossal number, do a modulo division by 7. And then, of course, that will give us an integer between 1 and 7, adding 1, of course, to change it from 0 to 6 to 1 to 7. And then we cast that. Remember casting? This is actually an explicit cast where we define the type, our enumerate type, that is, days of the week, that we want to convert this number to. And then that will then match up to the enumerate category as one of the days of the week. Okay, so if it returns, say, 5, that would then match with Friday. And then fry would be stored in day. But then, of course, when we actually output the value of that variable, remember that's still going to be the value of 5 rather than the actual word of fry or Friday. Okay, we'd actually have to define a string value rather than a integer value, which of course we can't do in C++, but we can in other languages. Okay, so that's a handy way that you can actually generate a random enumerate category. Here's a good example of that. And just before we move on, it's worth mentioning that there is an alternative form of casting within C++. We just talked about the explicit casting, where we would type the data type that we want to cast to within a pair of within a pair of brackets and then put that next to the data we want to cast, that's actually a remnant of the C language. That's what's called C-type casting. Okay, and of course C++ is supposed to be the increment of the C language. It's supposed to be the next version forward from it. Okay, remember plus is adding 1, so that's why C++ was named that way. It's supposed to be the increment of the C language for additional features and capabilities, and of course the object-oriented nature is chief among them. But anyway, in C++, there is this function called static cast. There's others as well, like const cast and dynamic cast and reinterpretation cast. But just sticking with static casting, it's another way of performing explicit casting. It's the function which is seen here, static underscore cast, and then within the pair of angle brackets, which of course is like generic types, we would write the data type that we want to cast to, and then follow that with a pair of brackets and have the data that we want to cast. Okay, as we did before. All right, but just a word of caution here, because no runtime check is performed on this, whereas that would happen in an explicit cast and obviously throw an exception. I think it does perform compile time checking though, so as long as the data is seen in advance of this static cast, as long as you're not getting it from the keyboard, actually this should perform fairly consistently. Okay, so just be aware of that if you're going to use static casting, or alternatively, if you're more comfortable with explicit casting, use that. But some programmers like to use static casting simply because it's easier to search for it. Okay, casting is well known for throwing up exceptions and problems when data doesn't convert easily. So having a keyword for static cast can be easily searched for, rather than all of the references to primitive data types, which of course will exist within return types of functions as well as variable declarations. Okay, so static cast is unique and can be searched for easily. Okay, so just be aware of that. Let's move on now onto the final topic, which is preprocessor directives. And so remember, in the previous presentation, we had a look at the #include directive, where we could actually include a reference to another class or a particular library that we wanted to draw from. Okay, and that was an example of a preprocessor directive. And so what that means is that these instructions are going to be executed before the rest of the code from the main onwards is compiled and ultimately executed. The clue's in the name, of course, because pre-processing means that it's going to take place before the processing of the code that's been written. And so the timing and order is important here, because if we've got references to other classes within our main function, then obviously we're going to need to make sure that those are referenced before we compile the code within the main function. So that's why the include directives were stated before compilation of the main function. Okay, but here we're going to have a look at an example of using some other preprocessor directives, which are useful in certain circumstances. We're going to see these in a moment, such as #define, #undefine, #if, and end-if, and also #else as well. So hopefully you can tell from that list that the preprocessor directives all start with a hash. That's one of the ways that you can tell whether it's a preprocessor directive or not. And of course they tend to be stated before the main function, and of course remember that they don't feature a semicolon. Okay, so let's have a look at an example then. Notice here that we're using the #define directive to define a macro, which will have a name and a size. So if you pay attention to the first blue box here, you'll notice that we've got #define and then size, which uppercase kind of infers a constant given the value of 100. And so that would be defined before the main function. And if, say, within the main function we had code such as the furthest left blue box underneath the before header here, if count is greater than size, that would then become if count is greater than 100, because the reference to size would be replaced with the value of 100. After the pre-processing has happened, the processing of the macro, the size being defined, and then once the main code has been compiled. But of course, I should caution you again here in saying that macro definitions of constants are not a good practice, because of course we don't define the type. Even though we can infer it's an integer through the whole number of 100, we don't define the type explicitly. And remember, C++ is a strongly typed language. So whilst this is a workaround to that, it's not good practice. Okay, so not a good idea. But it does at least demonstrates how macros can be used and the concept of using preprocessor directives. Having a look at this example here, this is better practice, where we're defining a particular state. In this case, it's Xbox, the gaming console, of course, and we're defining that before the main function. And then we've also got a conditional, basically the equivalent of an if statement, to say, well, if the definition is Xbox, then call a particular function of the controller referring to the state, and then of course hash endif to end the conditional if directive. Okay, so it's kind of the equivalent of an if statement, just taking place before the main code. Okay, so this would allow us to run a certain function if a particular state had been defined. Okay, on this slide here, notice that we've actually modified that example in the first blue box by immediately after defining Xbox, we then undefine it. So that means that the code inside that conditional statement would then be grayed out. Okay, it doesn't run that. And likewise, if we actually comment out the definition of Xbox in the last blue box here, again, that would prevent that code from being run before the main code is compiled. Again, it's all about timing and order. Remember, this is all taking place before the compilation of the main function and the rest of the code that you've written in other classes. And of course, we can extend the example by having an else preprocessor directive again here. So here we're providing the equivalent of an else part to the if statement, where we may want to run an alternative function in this case if the first condition is false. Okay, so this will function very similar to the normal if-else block that's within your code. The only difference here, of course, just to re-emphasize, is that this takes place before the compilation of that main function. Okay, so you can perform all the similar types of logic that you would do within your code before you actually come to compile that main code. All right, of course, this is quite useful for running optional parts of your code. Okay, it saves you having to modify the contents of your main function. You may want to just write a very simple test above the main function, as we're doing here, to run different parts of the code, different functions to perform tests. And that brings us to the end of the slides. So hopefully that's a quick introduction to the preprocessor directives, as well as all the other types of concepts that we've covered in this presentation. Let's now transition and have a look at some of the exercises. And I'll help you get started with some of these exercises. Let's have a go at the first exercise here, where we've got to create an array which holds 100 scores and also assign random scores to them between 0 and 100. So 100 scores, which will be between 0 and 100. And then I want to tally how many are between a certain range. So I've got a range here. One of the ranges is from 0 to 40. That would be one tally, the novice category, and then intermediate's 41 to 60, advanced 61 to 80, and then hardcore status is 81 to 100. All right, so there's a few things going on here. We're using arrays, we're going to be using random number generation, and also loops and property selection statements as well. So let's dive in and see if we can make some progress on this. So here we go. In right hand side, I've just got a new Visual Studio project. If you know what we did last time, just to save us having to write out standard library all the time, I'm just going to delete that and then refer to the namespace std, just to, it's short for standard library, just to save us having to refer to it all the time. All right, and hello world's a nice output for our first program. I'm just going to change that just to have a little reference. Say this is the first exercise here. Just do a little bit of formatting as well. There we go. Hopefully that will give us a good indication of where we are. All right then, and let's start by declaring a static array called scores. So remember what we said in the presentation. A static array is of fixed size. We declare how many elements that the array is going to contain. Hopefully you remember we have to declare what type of data we're going to be storing there. C++ is a strongly typed language, so I'm going to have my data type int, and then I'm given the name here called scores, and then afterwards is where I want to, within the square brackets, is where I want to define how many elements that this particular array is going to have. And in this case, we need 100. They'll be numbered from 0 to 99. And this should declare an array. It doesn't yet assign any values to it. We could do that, but that's going to take us quite a while to write them all out individually. Therefore, it might be much quicker to generate them randomly, which is indeed what we're asked to do in the next statement here. Within a loop, assign each random score between 0 and 100. Okay, so here we go. We get to test our ability to pick and generate random numbers. So let's have a go at this then. Hopefully remember I need to call the srand function. And then I actually need to pass it the number of seconds. Well, I could pass it, I don't have to, but I'm going to pass it. The number of seconds that have passed since 1970, January the 1st, 1970. Okay, just have a large number of seconds to pick a random number from. And of course, that's going to change every second, so that increases the chances of then choosing and generating a random number from that. Okay, so I need to write that once, even though it's tempting that you want to call it every time you then pick a number. It actually only needs to be called once. That will become evident in just a moment. Let's now set up a for loop to repeat 100 times for the 100 elements. Going to need to declare a temporary counter variable called I. Start it at 0 and then repeat whilst I is less than 100 and then increment. Okay, hopefully remember those are the 3 steps. And remember that we said for single body statements, we don't actually need to have a pair of braces. And I think for this particular loop, really all we want to say is we want to refer to the individual elements. We're going to loop through them from 0 to 99. That's going to be our 100 elements. And I'm going to refer to the loop counter in order to do that. Okay. And then all I want to do is assign a random number from that colossal number of seconds that we started with. And remember there's going to be a difference between referring to srand and rand. Srand provides the seed, the colossal number of seconds that have passed since 1970. And then rand draws from that, picks a random number from that. Okay. And just to reduce the amount of scope, so I don't have a colossal range of random numbers, remember we're only asking for random scores between 0 and 100. We can perform a modulo division where we basically take the remainder of that. Okay, so here, if we divide modulo 100, well, in fact, that's going to give me scores between 0 and 99, because if I divide by 100, that will go in perfectly. So maybe, actually, we should increase that to 101, just to get the full range from 0 to 100. Hope that makes sense. Regardless, this is just a single statement within the body of the for loop. Therefore, I don't actually need braces. If I found out later I need to add more, more statements, that is, I'd have to go and add a pair of braces to surround the statements within the for loop. But for now, I think I can get away without a pair of braces for this. And I suppose, depending on design, you may want to allocate these to different functions. That might be cleaner and look tidier. I think for now they will continue just in the main function, just to get everything set up. Then that can be extension work for yourselves to go and redesign this into more appropriate functions. Okay, and indeed that's what we're going to go on to look at, I think, in the next presentation as well. So probably best if we stick in the main function just for now. Okay, but better designs are available, just to say. Let's continue here. Now that we've assigned, hopefully we're going to assign random scores between 0 and 100 for the 100 elements, which are actually numbered from 0 to 99. But next, we're asked to then record the number of scores that lie between the following ranges within a second array named ranges that contains 4 elements that correspond to the tallies for the 4 categories. Okay, so these categories are not actually going to be named novice, intermediate, advanced, and hardcore within the integer array itself. We're going to have to match that in our own minds, but each of the elements 0, 1, 2, and 3 will actually store the tally for that, and then later we'll output them and we'll give a nice label for element 0 referring to novice, element 1 referring to intermediate, 2 referring to advanced, and then 3 referring to hardcore. All right, so let's set up this second array called ranges. That's going to have 4 elements. Okay, and I also see the note here to say that local variables are not automatically initialized with a default value. And because we actually plan to increment these, for every score that we find between these range, we're going to increase the value at that particular range element by 1. So just reading ahead and anticipating what's coming, I'm actually going to use the initializer here, and we looked at this in the presentation, by actually starting these elements at 0. Okay, so I can do that in C++ syntax. And then let's start the second loop. So here's where I want to look through all of those elements which we just assigned random numbers to. I could have a little comment to say assign random values for scores, or random scores if you prefer. And then here, that's also, we're going to be doing something similar. I suppose I could actually do it at the same time, but let's just in the same array. I mean, after I assign the score, I could then immediately increment the range. But let's just separate them for now. Again, this is just a first attempt. You might want to improve on the actual design of this a bit later, especially when we get to functions in the next presentation. But I think I'm going to use a pair of braces here because we're using quite a few statements, you'll see in a moment. So here's where I want to say, well, if the particular score that I'm looking at, I'm going to have to go through them one by one. So if scores I has a value that is between 0 and 40, so I could use logical operators there, or just shortcutting it, I could say, well, let's compare it with the upper bound. If that's the case, then we want to increase the first element, the value of the first element, for ranges. And that's where we'd say ranges 0 plus plus. Okay, that's going to refer to the novice category and then keep a tally for us. Okay, So let's do something very similar for the second category, which is actually ranges 1. That's where we're going to want to compare it against the upper bound of that category, which is 60. Okay. Yeah, ranges 1. And I'm also going to add an else if as well there, just for exclusivity. Let's also do the same for the upper bound of advanced, the actual third category, but actually that's going to correspond with element 2 of ranges. And then finally, I could have another else if, or I could actually just say else here, because that's going to be the last condition. So therefore, if all of the above is false, then it must be over 80. Therefore, and assuming it goes up to 100 only, therefore it must be the last category, which is going to be ranges 3, corresponding to the hardcore category. Let's also add a little comment here to say increment tallies, okay, for range, or increment range, you could say. And then finally, we just want to output them. Okay, so assuming all's well so far, we can then just have an output just to display the tally for each of the range categories. So let's say range is 0. And then let's do the same for the others as well. So let's say intermediate. You might want to include the range as well if you'd like, but I'm just to save time here. Advanced is the third category, but of course that's element 2. And then finally is hardcore, which is ranges 3. Okay, and again, there are better designs available, but just to get something up and running here, let's see if this works. Okay, good. It looks as if we've got a fairly good spread of numbers across the categories. We haven't actually printed out the contents of the scores. That could take up quite a lot of room. I guess you might want to think about how you do that, should you want to check the individual scores themselves. But I'll tell you what, let's run this again and see if we get a different arrangement. And we do actually notice those numbers change. So that gives us confidence that we are actually generating random scores each time. Okay, I think the number of novice scores will probably be larger, because you notice there's a larger range there of 40 scores that it could potentially be, as opposed to the others, which are in sort of 20s. So you might see a larger number of novice scores being generated. But hopefully, as we keep generating these, we do see subtle changes in these tallies here, which gives us confidence that they are random each time. Okay, so there you go. Hopefully that was a nice, quick and easy way to demonstrate how to get started with the first exercise. Have a go at this, and then have a go at some of the other exercises here, which ask you to implement preprocessor directives, enumerate types, and other things that we've introduced throughout the presentation. Okay, so give that a go and see how you get on.